9.9 functions by power series. So again, this focus is going to be with geometric power series. We're going to write the power series for a geometric geometric series, all right? And later on, we're gonna talk about differentiation and integration, okay? So if we're looking at this, you know, we're thinking of the sum as A over 1 minus R, right? If the sum of this geometric series, if it converges, right, it equals this A over 1 minus R. So this is kind of like our starting point here. Now, if we let A equal 1 and the R equal X, this is a power series for the function 1 over 1 minus X centered at 0. Okay, so we would say, oh, this is 1 over 1 minus X is equal to this power series where A is 1, R is X to the n power. So basically, we're going to create this geometric series, but it's going to have an X in there raised to a power, hence the geometric power series. Okay, so we're gonna just jump right into our first example. We're gonna find the geometric power series representation for this function, all right, centered at X equals 0. So our first focus is this function right here, okay? So our goal is we want this 4 over 3x plus 2 to look like this, A over 1 minus R, okay? Where our radius is going to be in terms of X. All right, so the first thing I'm going to do is I'm going to swap these two, and I'm going to say 2 minus a negative 3x in my denominator. So it doesn't change anything, but it's the start of getting it in this format. My other scenario is this value here needs to be 1. So what do we have to do to each term? Well, I need to divide that by 2, but to keep everything balanced, we need to divide everything by 2. So by doing so, we end up with 4 divided by 2 is 2, and then our denominator is 1 minus negative 3 halves x, okay? So this right here is our A value, and this right here is our radius, okay? So now we can go ahead and write our power series because we're in this format, okay? And we know that a geometric series is in the form A times R to the n, okay? All right, so now we're going to rewrite that in terms of the power series. So our A value is 2, our radius is negative 3 halves x to the nth power. So here's our power series. Now what we can do is we kind of clean things up a little bit, and just to make it look a little nicer and identify some things. So I'm just going to break up the numerator and the denominator. So we have that 2. This negative is going to be raised to the n power, then 3 to the n, x to the n. So we're really just breaking everything up over 2 to the n power. All right, so 2 over 2 to the n. Our denominator is just going to go to 2 to the n minus 1. So here is our power series for this function. Okay, but now what do we have to do? We have to figure out the interval of convergence. Okay, now since we're dealing with a geometric series, we have to talk about when a geometric series converges. Okay, so this time the interval of convergence isn't using the ratio test. All right, it's going to help us, or we're going to use the geometric series rules, okay? So we know that this converges when our radius, the absolute value, is less than 1. Well, our radius is negative 3 halves x, so when that's less than 1, I can essentially forget about this negative when we solve this inequality, all right? So we're setting up that inequality, multiply both, or all three areas by 2/3, and we get this right here. Now, if you were to test these endpoints into our power series, you're going to get a diverging series when we plug x equals 2/3. You're going to get just 2 times 1 to the n, all right? And then when x equals 2/3, we're just going to get an oscillating series, so that diverges. So typically with these geometric power series, the endpoints will always diverge. So our interval of convergence is negative 2/3 to 2/3, not inclusive. All right, now let's take a look at this next example where we're going to look at the geometric power series, or find the geometric power series representation for the function 3 over 2x minus 1. But this time it's centered at c equals 2. So how's that going to change the game? Well, let's go ahead and take a look and get this 3 over 2x minus 1 in the form a over 1 minus r. Okay, so the first thing I just rearrange, right? 3 over negative 1 plus 2x. But keep in mind, it says centered at c equals 2. So this portion here, I'm going to rewrite as this over here, all right? So I have to be centered at 2. So that's this x minus 2 portion. So what we need to do is we need this right side to equal negative 1 plus 2x, okay? So if I distribute this 2, because we have the coefficient over here, we're looking at 2x minus 4 over here. Well, I need this 2x minus 4 plus something to equal negative 1 plus 2x. So what needs to go in that blank? Hopefully we recognize that that just needs to be a 3, okay? So we can kind of go back to this round right here and pull it into our denominator, all right? So now, again, we're at the fact where we are centered at 2. But again, I need it in this form where this, in our denominator, that first term needs to be a 1. So what are we going to do next? Well, I'm going to take that 3 and I'm going to divide by 3 to make it a 1. Divide by 3, divide everything by 3. Okay, at the same time, remember it's got to be minus. So I'm going to have to say 1 minus, and then inside I'm going to have a negative 2/3 times the quantity x minus 2. And we have 1 in our numerator. So this guy is our a value, and this right here is our r value. So now we can go ahead and write that power series. Okay, so our power series, this function is equal to the power series, our a value of 1, times our r value, negative 2/3 times x minus 2, all raised to the nth power. Again, if we break things up, we've got this negative 1 to the n, 2 to the n, and then x minus 2 to the n, all over 3 to the n. You can certainly leave it in this sense, all right, no big deal, but if you're checking answers, you might see it written this way, okay? Now, lastly, we have to look at our interval of convergence. So again, since we're dealing with a geometric power series, we're using the geometric rules for convergent series. So the radius has to be less than 1. So the absolute value of negative 2/3 x minus 2 has to be less than 1. Dropping the absolute values and kind of forgetting about that negative because the absolute value, all right? Multiplying both sides by 3/2 and then adding 2 to all 3 regions, we get our interval of convergence. If you were to go back and test these endpoints again, you're going to see that both of those are going to diverge, all right? And so our interval of convergence goes from 1/2 to 7/2 non-inclusive. Okay, I want you to try this next example. You find the geometric power series representation for the function 5 over 5 plus x squared. It's centered at 0, so we don't have to do anything tricky like in example 2. So go ahead, try it on your own, and check back after you've gone through as much as you can. All right, so were you able to rewrite this in terms of a geometric series, a geometric function? All right, so I just rewrote, I rewrote it as 5 over 5 minus negative x squared, and then we need this to be 1, so you should have divided that by 5 and everything else by 5. Okay, so you should have gotten our a value to be 1 and our radius to be negative x squared over 5. And that's okay that it's an x squared, no big deal. So now when we go ahead and rewrite that power series, our a times r to the n of the series from n equals 0 to infinity, if you wanted to rewrite it as an alternating series there, you absolutely can. So now we have that, and the last thing we need to do is find our interval of convergence. Again, it's a geometric series, so in order to converge, the absolute value of r has to be less than 1. So you can really, again, I could have that negative x squared over 5. When we take the absolute value of it, that goes away. And so now multiply both sides by 5. When we take the square root, we're not going to take the square root of negative 5. We're taking the opposite of the square root of 5. Okay, so we are within this interval here. So our interval of convergence goes from negative root 5 to positive root 5, non-inclusive. The last examples deal with differentiation and anti-differentiation. So taking the derivative and taking the integral of a certain series. So suppose we have f of x, which is 1 over 1 plus x squared, and it's represented by this power series from 0 to infinity, negative 1 to the n, times x to the 2n. If we were to write out the terms, it's going to look like this. So our first goal is we want to use this power series to find a power series for g of x, which is negative 2x over x squared plus 1 squared. So what we should recognize is, oh, well, this right here is the derivative of this function here, okay? So recognizing that aspect is the first step. So what that means is, yes, we're going to take the derivative of g of x, we're going to take the derivative of f of x to get g of x, all right? So what does that mean? It means we need to take the derivative of this power series in order to get g of x, okay? So g of x represents the derivative of the power series that was given to us, okay? So we're going to take the derivative of this power series, all right? So when we do that, one thing we need to note is our index is going to change from n equals 0 to n equals 1. And then the same rules for differentiation apply. So this negative 1 to the n, that's just a constant or a coefficient. We bring that power on down, so 2n, x to the 2n, and we subtract 1 from the power. Okay, now we can go ahead and change our index back to n equals 0. So by changing this decrease, so going from n equals 1 back to n equals 0, we have to offset it by increasing n to n plus 1 everywhere we have an n in the original derivative. Okay, so when we clean that up, we're going to get the series from n equals 0 to infinity of negative 1 to the n plus 1 times 2n plus 2 times x to the 2n plus 1. All right? So then one last thing, we need to find the interval of convergence. Now, since this is not a geometric series, we have to use the ratio test to determine the interval of convergence. Okay? So I just quickly set up that ratio test. Remember, it's 2 times n plus 1 plus 2 over 2n plus 2, x to the 2 times n plus 1 over x to the 2n plus 1. So this is just setting up the ratio test. When all is said and done, we're going to get the absolute value of x squared. Has to be less than 1. Going through that, we're going to get our interval of convergence to be negative 1 to 1, non-inclusive. All right? Okay, so then our last example is going to deal with integration, okay? So we're going to use the power series to find use a power series to find the power series for h of x, which represents the arctangent of x. Now what we should notice is arctangent is really the integral of 1 over 1 plus x squared. So by recognizing that aspect, okay, that's key. So we know, all right, we just need to integrate that power series. We need to integrate the series that was given to us, all right, to represent a function for arctangent of x. So by integrating this series, the same integration rules apply, okay? Again, this negative 1 to the n, that's just our constant. So we have the series from n equals 0, we don't need to change the index, I'll talk about that in a second, to infinity of negative 1 to the n. Now we have to add 1 to the power, 2n plus 1, but then we have to remember we have to put everything over that 2n plus 1 to negate everything. And then don't forget we have that plus c on the end. We just wrote it in the beginning this time. Now with integration, the nice thing is we don't have to change this index because this plus c takes care of that aspect, okay? So that takes care of that index change. So now again, the last thing we have to do is find our interval of convergence. So since this isn't a geometric series, we are going to use that ratio test. So setting up our ratio test, the limit as n goes to infinity of this quantity, it's going to whittle down to the absolute value of x squared, which has to be less than 1 in order to converge. Solving that, again, we would get our interval of convergence to be -1 to 1, non-inclusive. All right, so if you have any questions on functions by power series, let me know.